Hey Opties! Today we're talking about graphing rational functions. We've talked about rational expressions, which means we've got a fraction and the numerator and denominator are polynomials. And we've also talked about rational equations, where we've got one rational expression equals another rational expression. Today we're talking about how we're going to look at those as actual functions, and we're going to focus on graphing. So let's go ahead and take a look. Domain. That's something that will help us do our graphing, and it's just something also very worthy of talking about with rationals. Remember that domain is everything that x is allowed to be. For rational functions, we write this in interval notation. How to find that? Rational expressions have denominators, which is a domain danger zone, since 0 cannot be a denominator. So any restriction for the rational expression that is making up that rational function is not included in the domain of the rational function created by that rational expression. So let's look at an example here on example A. Looking at example A, we see that there's no more simplification that can be done for this rational expression that makes up our rational function. And we can tell it looks like a function here because it's got a y equals. That's what's making up our function here. So what is the domain? We want to find the restriction or restrictions. So we set our denominator equal to 0. So x plus 1 equals 0. And then we figure out what x equals, which is -1. And that's what x cannot be. So x cannot equal -1. And if you would like to just think about it as starting out by setting it not equal, that way you don't have to do any switching at the end, you can do that as well. So how do we actually write what our domain is? So our x can be anything it wants to be as long as it's not -1, because that's the number that will make our denominator equal to 0, because we'd have -1 plus 1, which is 0, and we can't divide by 0. So instead of having our domain just be -infinity to +infinity, we've got to make a break on the inside of this. We've got to make it break at -1. So that means we're going to go from -infinity up to -1, and we say up to, which means we're going to have that parentheses here instead of a bracket, because we can't equal -1. We can just go really close to equaling it. And then we want to start back at -1 and then carry on to infinity. So when we make this break here, we still have to put them together, and we put this U here called a union. So we're putting them together, and we're putting that little break in between our all real numbers domain just to show we're going to exclude this -1. For example B, we can see there's some simplifying that can occur here. So let's go ahead and simplify it. The numerator is a difference of squares, and it's going to factor to x plus 4 times x minus 4. And remember, a difference of squares looks like this and equals a plus b times a minus b. So that's how I was doing that factoring there. Now let's factor our denominator. Factors of -12 that add to 1. That's going to be 4 and -3. So we see that we do have a factor that simplifies to 1. So our final simplified version is x minus 4 over x minus 3. Now, technically we didn't have to factor this because it's only asking for our domain, and we really only have to look at our denominator. But we were going to have to factor our denominator regardless to figure out what x cannot equal. So we just went ahead and did our numerator as well. But it's good practice to factor and to simplify because you do that a lot anyway. So let's go ahead and finish up our domain. by figuring out our restrictions. So if x plus 4 times x minus 3 is our denominator, it cannot equal 0, so x cannot equal -4 and +3. So these are the numbers we're going to exclude. Notice there are two numbers. So we're going to have to make a break in our -infinity to +infinity, and we have to make two breaks. We're going to have to go up to -4 and then go to -4 to 3 and go from 3 to +infinity. So let's start at -infinity. Then we're going to go and hit the -4 to 3 and then hit the 3 to infinity. So yes, there are three pieces here, and you'll have three pieces if you have two solutions here. If you have only one solution, or one restriction, I should say, then you would have only two pieces. So only one union, but two pieces. And here we have those two unions and three pieces. Next, let's talk about asymptotes. Yes, it's a funny word. It's kind of crazy looking even when you spell it. Again, that's asymptote. So definition is a line that approaches a curve but never meets it. So you get really, really close to the curve. Remember just a moment ago when we said we're going up to our -1, which is our restriction, but we can't ever reach it, showing that with our parentheses instead of a bracket. That is going to be directly related to our asymptotes here. So we've got two different kinds. We've got a vertical asymptote and a horizontal asymptote. So you could have more than one of these. You could have one and not the other, blah, blah, blah. So let's look at a vertical asymptote. Any restriction that exists after simplification is an equation of a VA or vertical asymptote, and that's going to be x equals a number. Think about if you have x equals number and you graph that, it's always a vertical line. Other restrictions are called holes. So yes, it does disrupt your domain. As you can see, even though we simplified the factor x plus 4 to 1 here, it wasn't there in our simplified version. However, it still was a restriction and it got counted out of our domain. But those are called holes. It is a type of discontinuity would be the word we use to show it's kind of disrupting our domain. Okay, so we also have horizontal asymptotes, which are a little bit more of a beast. We don't worry about these as much in Algebra 2, but I did want to at least expose you to it, just so you've heard it. And we will be seeing these lots on graphs, but to algebraically find them, we're not as concerned about as being able to do that with a vertical asymptote. So horizontal asymptotes, if the degree, which means the highest exponent of the denominator, is greater than that of the numerator, the horizontal asymptote is y equals 0, and these are all y equals. If the degrees are equal, the horizontal asymptote is y equals the ratio of the leading coefficients. And leading coefficients means the numbers in front of the terms that have that degree on them, that have the highest exponent. And the third way you can tell is if the degree of the denominator is less than that of the numerator, there is no horizontal asymptote. So let's look at example C here. Let's look at our asymptotes, and then we're going to do a quick graph of our function, because if we know our asymptotes, it makes graphing pretty easy, really, even though it looks kind of funky for rational functions. So let's look at vertical asymptotes first. So remember, we're looking for restrictions that only exist after simplification. We don't see any quadratics here. We don't see any factors being multiplied where we might go ahead and simplify a common factor. This is fully simplified. So we simply just need to look at our denominator, set it equal or not equal to 0, figure out our restriction, which is x equals -3. And it's a restriction that's there once our simplification is complete. So then you would switch it to equals. So The only thing that's really different than a vertical asymptote and a restriction is that one, it only exists if it's there after simplification, and two, it's actually an equals, because your function can never reach this. It's just getting very, very close to this line, which is why it's called an asymptote if you look back at that definition. So let's go ahead and graph this, and we'll do it dotted. So x equals -3 is right here, and that's gonna look like that vertical line. And we call it dotted because it's not a piece of our function. It's just showing us kind of how our function is going to be shaped around this vertical asymptote. And let's find any horizontal asymptotes that exist. Let's look at our degrees of our numerator and denominator. X is our only term here, and its exponent is 1. X is the term with the highest exponent in our denominator, and its exponent is 1. So the degrees match. So we just find the ratio. So those will go to 1, and that's just a 1 over 1. So 1 over 1, which of course is 1, is the equation of our asymptote for horizontal, and of course that's going to be a y. So y equals 1 is our horizontal asymptote. So let's graph that. Here's y equals 1, and we'll do a dotted line. Okay, so we've really got the building blocks to graph our function. One thing I want to talk about before we graph it is the difference between a positive rational function and a negative. So let's say we have 1 over x, and here's our xy plane here. This function looks like this. It's got a horizontal and vertical asymptote of 0. And it's got a piece in the third quadrant and the first quadrant. Now what happens differently if you have -1 over x is it's very similar, but it looks like this. And yes, I know I'm using the same graph, but what I want to show you is for this one, the quadrants it takes up are the same quadrants it would take up if you just looked at the line with a y equals x, which I think of as a positive slope. And if you think about the line y equals -x with a negative slope, that's going to be looking like taking up the second and fourth quadrant. So then you can remember that a negative rational function takes up these two areas. So here's what I mean. Our function we're looking at is positive, okay? So that means when we approach our asymptotes here, which looks like this, getting really, really, really close to -3 and to +1 here, we're gonna go in this area and this area, opposed to drawing our pieces of our function here. Easy ways to tell that are to look on Desmos, or you could plot yourself some points by picking some x values and doing some function evaluation and figuring out your y's. All right, Opties, that's it for graphing rational functions, including discussion of domain and our vertical and horizontal asymptotes. See y'all next time.